In number one, we have an improper integral. It's called an improper integral because one of the limits is infinite. So what we're going to do is we replace that infinite limit with a variable, let's say r, and we take the limit as r goes to infinity. Okay, so let's integrate using the power rule. X to the minus 1/3 plus 1 is x to the minus 1.3 plus 1 is x to the minus 0.3, or let me write it as x to the minus 3/10. And then we're going to divide by minus 3/10 or multiply by negative 10/3. All right, and let's evaluate between 1 and r, and we take the limit. Okay, so we have limit all right, now substituting in, we have 1 over r to the 3/10 minus 1 over 1, or 1 to the 3/10, which is 1. Now when we take the limit as r goes to infinity, this fraction is going to 0 because the denominator is going to infinity. So this integral is equal to minus 10/3 times minus 1, or 10/3. All right, so we have a finite number, so we say it converges. Okay, we're going to do the same thing in number 2. We'll take the limit as r goes to infinity. And here we have x to the minus 4/5. So let's do the power rule. And we have minus 4/5 plus 5/5 is 1/5. So we have x to the 1/5 divide by 1/5, or multiply by 5. And let's substitute in the limits. So we have r to the 1/5 minus 1. Now we're taking the limit as r goes to infinity, so this first term goes to infinity. So we say that this integral diverges. In number 3, we have a different type of improper integral. This limit of integration is not in the domain of the integrand. It makes the denominator 0. So that's why this is an improper integral. So this time we'll take the limit as r goes to 7, and we'll replace 7 with r. I should mention that r is going to 7 from numbers bigger than 7, so we could put a little plus sign here, meaning r going to approaching 7 on the right, because this is a limit between, this is an integral between 7 and 10. All right, so the values are all larger than 7, so that's why we're approaching 7 from the right. Okay, so let's integrate this. And here, instead of, let's write this in exponent form instead of this form, so that we could use the power rule. I'm not going to do a u substitution, since if I place u equal to x minus 7, du is equal to dx, so I'm just going to use the power rule directly. All right, so we have x minus 7 minus 1/2 plus 1 minus 1/2 plus 2 over 2 is 1/2. And if we divide by 1/2, that's multiplication by 2. All right, we're ready to substitute in the limits. And first we'll put 10 in. 10 minus 7 to the 1/2. And subtract r minus 7 to the 1/2. So as r goes to 7, this is going to 0. This goes to 0. And here we have 3 to the 1/2. This is 3 to the 1/2. So this limit is equal to 2 times the square root of 3. All right, a finite number, so we say this converges. All right, in number 4, we are going to start the same way, replacing infinity with r. And let's write this as 2x squared plus 5 squared, so that it looks like an arctan derivative. So we'll integrate this. And if we did a u substitution, we'd put u equal to 2x, and du is 2dx is 1/2 du, so 1/2 comes out in front. So rather than doing the u substitution, I'm just going to bring that 1/2 out in front. All right, so this is equal to 1/2 times 1/5 arctan 2x over 5. And we're going to now substitute in our limits. So first we have arctan 2r over 5 minus arctan 0. As r goes to infinity, this is going to infinity, and arctan is going to pi over 2. All right, we get that from, if we remember what the graph of arctan looks like. Let me just draw that quickly. The graph of arctan, y equal arctan x, has two horizontal asymptotes, one at pi over 2 and minus pi over 2. It goes through 0. It goes up to pi over 2 and down to minus pi over 2 on the left, up on the right, down on the left. So as we go to the right, the graph goes up to pi over 2, so that's what we have here. And this, an arctan 0 is 0. We see it goes through 0 at 0. All right, so this is equal to 1/10 times pi over 2, or pi over 20. The integrand in number 5 is a typical integration by parts. We're going to put u equal to x and dv equal to e to the minus 2x dx. Okay, so let's do that. All right, so we're going to start by, let's just ignore the limits for now, and let's just integrate this. Okay, let's just integrate this, ignoring the limits. So we'll put u equal to x, and we're going to put dv is equal to e to the minus 2x dx, and du is equal to dx. and v is equal to minus 1/2 e to the minus 2x. And now integration by parts formula, uv minus integral v du. There's uv minus 1/2 x e to the minus 2x, and then minus v du. So that would be, we have two negatives here, so I'm going to make that plus 1/2 e to the, plus 1/2 integral e to the minus 2x dx. All right, now let's do that second integral. And here we have a 1/2, and then a minus 1/2 is going to come out in front, so that's going to be a minus 1/4. All right, now we're going to look at, now we're going to put in these limits and look at the limit as r goes to infinity. All right, so now we're looking at the limit as r goes to infinity. Okay, minus 1/2. I'll put the x on top and e to the 2x in the denominator here. And here I'll write the second term as 1 over e to the 2x. Okay, let's substitute in our limits. Here we have r, e to the 2r, 1 over e to the 2r. Now substitute in 0, and here we have 0, and here we have minus 1/4. Okay, now as r goes to infinity, this is definitely going to 0. What about this quotient? This quotient, numerator is going to infinity and denominator is going to infinity. This is going to infinity over infinity. So this is a limit that on which we could use L'Hopital's rule. And we'll do that in a minute, but we'll see that if we use L'Hopital's rule, this goes to 0 as well. Okay, I'll do that in a minute, but let's assume that's true for now. And so this is 0, and so the whole thing is equal to minus 1/4 or 1/4. All right, let's just do this limit here, this first limit that we circled. Limit r goes to infinity, r over e to the 2r. Well, this is of the form infinity over infinity, so we're going to use L'Hopital's rule. Take the derivative of the top with respect to r, so that would be 1, and derivative of the denominator is 2 e to the 2r. So now this is no longer of the form infinity over infinity, it's of the form 1 over infinity, and this goes to 0. All right, like we said over there. All right, so this evaluates to 1/4, so it converges. Converges to 1/4. All right, number 6 is an interesting problem because if we look at this integrand, we could, let's first examine the end behavior of this integrand. So as x goes to infinity, the integrand x over x squared plus 3 is going to act like x over the square root of x squared. We just take the higher order terms. All right, to figure out end behavior, and that's x over x, which is 1. So what this shows us is this integrand is not dying down to 0. So just from that fact, we know that this definitely does not converge. This definitely diverges. All right. Okay, let's integrate it. It's not hard to integrate. And we'll see that it diverges. In order for something to converge, this has to go down to 0 pretty quickly. All right, so let's do this. Let's look at this integral. Okay, we could integrate this using a u substitution. If u is equal to x squared plus 3, then du is 2x dx. We're just missing the 2 over here. So let's integrate this using the power rule. Let me write this with an exponent of minus 1/2 so that we get ready for the power rule. All right, like I said, we're just missing the we have a derivative of x dx here. We're missing the 2. The derivative of the inside is 2x dx. So we're going to integrate, and we're going to put a 1/2 out in front. Integrate with the power rule. All right, so there's our 1/2. And here we have x squared plus 3 to the minus 1/2 plus 2 over 2. So that's 1/2 divided by 1/2 or multiply by 2. And now we have our limits of integration 1 to r. So we see that this expression does not end up in the denominator. It's definitely going to go to infinity. All right, so whether we have r squared plus 3 to the 1/2 minus 1 plus 3 to the 1/2. As r goes to infinity, r squared plus 3 to the 1/2 also goes to infinity. So, like we expected, this integral diverges.